Okay, welcome to the lesson on the limit of a function, part 2. So we saw in the first part, we kind of came up with a little bit of a definition, and we saw an example of limits. So what we're going to do is look at 3 examples. We saw an example in the first case where you had a function, and this was sort of the uninteresting case where, well, it wasn't uninteresting, but where the limit and the function were equal. If you remember, in this case, f at x, or f at a, whatever, f at a was equal to the limit as x went to a of f at x. And that was the case where you might have said, okay, well, why did we need the limit? We could have just subbed in that value, and it turned out it was the same. But then we saw another example where we had a hole. I guess I need to draw the hole. So there will be our hole. Put it right there. So we had a hole at a. So you couldn't evaluate the function, but the limit still existed. So in this case, f at a did not exist. And then there's a third case where limits can exist. So f at a could exist, but you could still have a hole. So I have a hole there. And the limit would be here. But the function is defined differently at a. So f at a is up here. So f at a exists, but limit as x goes to a of f at x does not equal f at a. Okay, so these are always a limit can exist. We're going to see in a bit ways limits actually do not exist. So sometimes you get functions where the limit doesn't exist. So let's go to something new. Okay, before we get into that, let's just quickly talk about one-sided limits. So we've really actually already done this. So a one-sided limit, if you remember when we were did the example where we did the chart, we took numbers a little bit below and then a little bit above. So when we were looking at limit as x goes to a of f at x, if you remember when a was 1, we took numbers like 0.9, 0.99, so below 1, and then we took numbers above. Those are really one-sided limits. So a one-sided limit, you have a left-handed limit, or a left-sided limit, and a right-sided limit. So really all that means is limit left-sided means numbers below, and the way we write that, almost the same, except now we put a little minus sign above, to the power of a. It looks like to the power, and then it's like a superscript, and then for a right-sided you put a little plus sign. So left-sided meaning from below, so minus meaning a little less, and plus meaning a little more. So this concept of one-sided limits is really fundamental to our definition of when a limit exists. So I'll write that right here. So a limit is said to exist if this left limit and this right limit are equal. Both exist and are equal. If limit as x goes to a from the left of f at x, if limit as x goes to a from the right of f at x. So if these two limits from the left and right are equal, Okay, so again, probably an example is going to help us see what that means. So let's take as an example, let's take a function that looks like this. Let's go with x plus 1. Let's go with x squared plus 1 if x does not equal 0 and let's go with 2 if x equals 0. Okay, so let's graph what this looks like. So x squared plus 1, you know what that looks like? Parabola, shifted up 1. But then at 0 we're going to have a hole because when x equals 0, it does not equal that. And then when x equals 0, the function's actually equal to 2. So we've defined this, sort of piecewise. That was x, that's y, that's f of x. Okay, so now let's think about the limit as x goes at 0 from the left of f of x. So there's two ways you could do this. You could look at the graph and say, what is the function approaching as we approach 0 from the left? And you can probably see it's approaching this number right here, right? It's going towards 1. When it gets to 0, it jumps up to 2, but we're never getting to 0. So this one would actually be 1. And then if you didn't have the graph, you could always do a table, right? Do the table x, f of x, take numbers a little bit less than 0, like 0 0.9, 0 0.99, 0 0.999, and sub them into this equation. We're using this equation because if x does not equal 0, which it's not equal to, oh, sorry, I put the wrong numbers here. These numbers should be getting closer to 0, not 1. Okay. I had that last example in my head. So we want them to get closer to 0, so 0 0.1, 0 0.01. Right? So that's getting closer to 0. But we should actually, for the left limit, we should be going from the negative side. And then what would be happening? So you'd see that this would be approaching 1. And then we could do the same thing from the right. And again, from the graph, you can probably see that it's going to 1. If you didn't have the graph, you could take numbers a little bit bigger. And then again, you'd see that it's approaching 1. So notice the left and right limit are equal. So therefore, the limit as x goes to 0 overall, right, is of f of x is equal to 1 because the left and right side, or left and right hand limits are the same. I'll write that because limit as x goes to 0 from the left of f of x equals the limit as x goes to 0 from the right of f of x, which is equal to 1. So since they're both equal to 1, the overall limit equals 1. Okay, so well, when does it not exist? So let's do one like that. So g at x equals, again we're going to do piecewise, we're going to go with x plus 1 if x is less than or equal to 1, and x squared if x is bigger than 1. So let's do a graph. Well, okay, there's my graph, but I'll do the limits first. So I'm going to go to 1 from the left of g at x, and I'm going to go at 1 from the right of g of x. So, from the left, which piece am I going to be traveling along if I'm going at 1 from the left? Well, 1 from the left means numbers smaller than 1, so I'm going to be looking at this piece. So it's going to be the limit as x goes at 1 from the left of x plus 1. And then you could do your chart, or you might even be able to see if you had to do your chart, you'd be taking numbers a little bit less than 1 and subbing them into there. And then hopefully you can see that that was equal to 2. And then do the same thing for this one. But now we're traveling at 1 from numbers bigger than 1, so that would be this piece, right? Because x is a little bit bigger than 1. So g at x would be x squared for that, and then this would be approaching 1. So here's, if you wanted to graph this function bigger than 1, you would have x plus 1. So x plus 1 looks like that, but we're only doing it bigger than or equal to 1. So it's just that part, and then, oh, sorry, control, I do the wrong part, right? This was less than 1, so we'd actually be below. It's this part, right? It's not the above part, it's below. And then bigger than 1, that's where we have a parabola. Parabola looks like that. But we're just, oh, sorry, that should be an open hole. So that's the parabola. So the function looks like this. So you can see that as you go at 1 from the left, you're approaching this number, which is 2. As you go around from the right, you're approaching this number, which is 1. So therefore, the limit as x goes at 1 of f, oh no, it's g at x, does not exist, because the limit from the left of g of x did not equal the limit from the right of g of x. Okay, so that's an example where the limit does not exist.